Okay, so continuing with the discussed examples, practice question 2 is easy. If you get practice question 1, this should be no problem. So you have saturated water vapor. Remember where that is on the diagram. It has a mass of 5 kg, 300 kPa. It's heated at constant pressure. So this is easy. The question tells you that it's constant pressure until you reach some final temperature. Calculate the work done. So of course, work done here is P V2 minus V1. Okay, it's water vapor, so you can easily find the V1 equals to Vg at 300 kPa until it reaches 200. So you find out 300 kPa and 200 degrees. This is already a vapor. So let's see, TV diagram. We have this. Okay, so initially it should be here because it's saturated vapor. Okay, and this is the T set, whatever the value is. You can go to table A5 and find out. Of course, this whole line is constant pressure. So you heat it up at constant pressure. So the path will follow this constant pressure line. So heating it up, of course, temperature has to go up. So the only way it can go is along this curve. So let's say it stops here. This is your T2. Okay, so obviously this is superheated region. So V1, no problem. V2, just take the pressure and temperature, table A6, find V2. Mass is given, pressure of course is given, no problem, you can find this value. Okay, the solution is here. You can pause and take a look. Question 3 also is constant pressure, and when you have, you can pause to read the question. When you have a piston that is free to move, then that means it's not restricted. Okay, you have this piston, it can move up as much as it needs to, it can move down as much as it needs to. Therefore, you have no problem like what you had in practice question 1. There was a set of stops, so it's not free. Okay, so this is quite an important statement. Its mass is such that it maintains the pressure, so this tells you that it's constant pressure. The only difference here is that it's refrigerant. Okay, so you have a different set of tables to look at, and you are given initial volume in liters. You're not given mass, you're given volume, so you have to find the mass, I'm sure. So also give yourself a challenge. Okay, try to solve this. The solution is in the next slide, and of course if you have any problems you can ask in our class after this. Okay, now practice question 4 and 5 are a bit different because they are dealing with, if you recall, isothermal ideal gas. So we have seen only refrigerant and water, which are both not ideal gases. So here you're dealing with air. First indication to tell you that you have to use a different approach. Okay, so you have air at this state, it's compressed to final pressure. During the process, heat is transferred from the air, that means it's cooling down, such that the temperature inside remains constant. There you go. That's your isothermal ideal gas. Okay, isothermal ideal gas, because of air and constant temperature. So remember, here you have options to solve. Okay, so if you're referring to the solution, the boundary work will be, you have this equation. Okay, and I also explained to you that P1 V1 can be replaced with P2 V2 or MRT. For reasons for this, you can go to the video previously, I think the last 2 videos maybe. Okay, V2 over V1 can be replaced with P1 over P2. If you're wondering how to know which one to use, because in this question looks like they use MRT here, okay, this and P1 P2, they're not using this at all. Why? Because these are the available information. You have M, you have R, you have T, you have P1 and P2. So use what you already have. Okay, so it should look like this, and then you can solve and you get this answer. So it's a negative because it's compression. So why we can't use area under the curve, why we can't use the constant pressure formula, because this is how the process looks like. Okay, I already discussed about this in previous videos. It's impossible to calculate this without doing the integration. Okay, so the ideal gas equation have given you the solution. Alright, yes, you know this came from the ideal gas. So question 5 is similar. You can take a look at it, okay, and ask if you have any parts that you are still not clear about. Alright.